All right, let's continue our discussion. So far in law of large numbers, our discussion was on um, x bar getting close to mu. It was all about average, right? Let's make it a little bit spicier and talk about sampling variation. So here's an example. Example says I'm going to go over it very quickly. This is the introduction to central limit theorem. All it says is that, look, this is my population's average. From this population, let me take samples of size at 3, 4, 5, and look at its distribution, all right? And that's exactly what has happened. I have taken sample of size what? Sample of size 5, all right? And let me look at distribution of x bar. Let me see what happens in this sampling, right? What happens is that I take a sample of size 5, I record its x bar. I take another sample of size 5, I record another x bar. I take another sample of size 5, I record x bar. And then I plot histogram of these values of x bars that I've got. All right, we are going to see how we can implement it in Python. Now, in Python, it looks, oh my God, so scary, but it really, the idea is very, very simple, all right? So the idea here is that let me plot a population versus sample mean. Look, that is population, gray one in the back, and this is a distribution of X bar or histogram of X bar when sample size is 5, all right? Observations, first of all, they peak at the same time, roughly about 76, all right? They peak in the middle, right in the middle. They peak together. Secondly, X bar, sorry, X bar has X bar has lower variance, lower spread. All right, that's not random. That comes from central limit theorem, and well, not necessarily central limit theorem, from distribution of X bar. Right. So let's move forward. Here is a sample of size 30. All right. The blue one is a sample of size 30. Again, sample of size 30, it gets even more squeezed around the mu, right? If we repeat this, we are going to get more and more condensed around roughly about mu, right? This comes from, to some extent, comes from central limit theorem and distribution of X bar. This is what we are doing. I have a population. From that, I have a taken of sample of size n, another sample of size n. The difference is that here now sample size is fixed, all right? I fix the sample size. And then I look at distribution of some form of statistics. What is that statistics? An example I had, my statistics in this example was X bar. I looked at distribution of X bars. How do I look at distribution of X bar? Well, I look at distribution of X bar by looking at its histogram. All right, that's as simple as it gets. All right, and let's look at expected value. Let's look at distribution of X bar. Expected value of X bar is mu. And how about variance of X bar? Variance of X bar is going to be equal to sigma square over n. You can do the calculation, you are going to get it. So sigma of X bar, sigma of X bar is sigma over square root of n. All right, so there you go. Here you have the answer, and we haven't even touched the central limit theorem. All this says, it says, look, X bar has the same average as mu. Right? Expected value of X bar is equal to mu. Where was that? Right here. How about the variance? Well, variance of X bar goes down as sample size goes up. So if n goes up, variance of X bar is gonna go down. All right. That explains by increasing n, you are getting all your histogram in a much denser interval. All right, because by increasing n, your variance goes down. All right. That is distribution of X bar. Now that distribution of X bar, we call that sampling. That X bar we look at. I'm sorry, I'm getting tired. X bar we call that mean, and looking at distribution of X bar, we call that distribution of X bar sampling distribution of sample mean. All right, sampling distribution of sample mean. So we looked at its parameters. How about its distribution? Again, I looked at mean of X bar, I look at variance of X bar. Those are just parameters of x bar distribution. How about shape of distribution of x bar? Well, that one will be given by central limit theorem. What does central limit theorem says? It says, look, and I'm going to be a little bit mathematically inaccurate right here. X bar has a roughly normal distribution. All right. In other words, x bar minus mu over its standard deviation. What is standard deviation of x bar? Sigma over square root of n. It says this one has a standard normal distribution, and we are going to experience this. Right? We are going to experience this one. Here are just a few examples, and in the next video we are going to see and experience this with Python. If my population, underlying population, is uniform of 0 and 1, and I take samples of size 10, this is sampling distribution of x bar. You see that it's roughly normal. If my population is, underlying population is discrete uniform, rand int, between 1 and 10, and you take samples of size 10, you see that this is not uniform anymore. This is normally distributed, roughly speaking, right? And the interesting thing is that this is discrete uniform. So central limit theorem holds that when your underlying population is discrete or continuous, despite the fact that normal itself is a continuous distribution. Even when your underlying population is is very different than normal. For example, if it's exponential with average of 3, and you take samples of size 20, this is distribution of, or histogram of, x bar. All right. Is sample of size in the statement of where is it? In the statement of central limit theorem, it says your sample size must be bigger than or equal to 30. Is that really required? Well, if we go back, for example, in uniform, you see that I took sample of size 10, and it looks like x bar is normally or bell-shaped distributed. When I have look at discrete uniform with parameters of 1 to 10, I take sample of size 10 and it works. Exponential sample of size 20 and it looks like it is bell-shaped or normal. It works. Is it really necessary to take samples of size bigger than 30? Well, yes, because I don't know the true shape of underlying population. If I know underlying population has a specific shape, then a lot of times n bigger than or equal to 30 is not required. But because I don't know that information, then I'm going to be stay on the safe side and take samples of size at least 30. All right. These are just examples. I'm going to move forward. Practice of all of this, just for the sake of time, I'm going to leave it to you. We are going to discuss good number of them in class, all practice problems. In the next video, I'm going to walk you through implementation of or experiencing central limit theorem yourself in Python.